We're going to look at another example involving the line integral, and this example is going to further investigate the concept of a piecewise smooth path. So as we've seen in both the book and in previous instruction, the concept of smooth or a smooth curve is introduced in a first semester calculus course. Piecewise smooth, we'll call it the non-textbook definition, is if the curve isn't smooth by itself, perhaps you could cut it into pieces where each piece is smooth along an interval. And I wanted to take advantage of just practicing some of the fundamentals that I use in my class. There are many types of curves you could focus on. In fact, there are infinitely many types of curves. So in my classroom, I have a few that I really focus hard on getting some foundation in there, and those that use these concepts in later, most likely physics courses, you'll see the curves could be quite a bit more interesting. So here is our piecewise smooth path. We're going to start at the point 5, 0 and go to the point 0, 2. These are x and y values, and we're going to go along this graph. This graph would be an ellipse, and I'll show you that these points are indeed on this ellipse in just a moment. And then once we get to 0, 2, we're going to return to this starting point, but we're going to return along a line. And ideally what we're trying to do is we're going to set up the line integral for work. This is one notation for that. I call this sort of the shortcut, but not quite a formula unless you're very, very comfortable with the notation and its little subtleties. So let's go deeper into this piecewise smooth path. All right, I have it pre-drawn for us. This is part of the ellipse. Starts at 5, 0. It would go to the y-intercept 2, to -5, to y-intercept -2, and then back to 5, 0 again. If we were to go all the way around the ellipse, we want to go in particular from here to here, and then the line from 0, 2 and returning to 5, 0 would just be that path there. So you can see that at both of these points, 5, 0 and 0, 2, maybe it's not smooth there, but each piece would be considered a smooth curve. And to evaluate or set up integrals for work, we would just set up two separate integrals and add them together afterwards for the total. Now, let's see what else I've got cooking here. Oh yes, the actual question. We'll just leave our path there. Given a two-dimensional vector field, first component and second component, x plus 3y comma x squared, we will set up, but we won't evaluate in this video, the line integrals for this evaluation. Remember, there's another way to write that. You have your vector field dot product the velocity vector with respect to t. This is a dot product of two vectors here. I call this more or less our formula that we use, and we've done quite a few up to this point. So notation wise, in case you need a reminder, this is one notation for a vector, and it could be written x plus 3yi plus x squared j. And then in linear algebra, there's definitely another way to write this, and those are just some of the options available. I like writing it this way in my classroom because it's compact and it more clearly shows when there's a 0 as a component. But this is very, very common, especially in the world of physics, so I don't mind which notation my students choose. In fact, I suggest just pick one and get good at it. Now, about our line integrals. Let's see what we can do here. All right. Ellipse. Well, we have a version of the ellipse that we've already worked on before. We'll call it a circular version of it. 5 cosine t, 2 sine t would be the entire ellipse if we allowed it to evaluate from 0 to 2 pi. But we only need it to go from here to here. So t, or sometimes it could be called theta, would be from 0 to pi over 2. This is a curve we've used before. I am not reteaching why that is an ellipse here. That's been previously done. Now, the line from 0, 2 to 5, 0, that would be starting at x is 0 and going right 5 places, and starting at y is 2 and going down 2 places. And if we write it this way, that would all happen as t is evaluated from 0 to t equals 1. There are other ways you could write that line, but this is the quick and easiest way to write a line. If you know a starting point and a next point to go to, there really isn't a method that's faster than that. It's very similar to the point-slope equation of the line we learned in algebra. Now, in order to do line integrals, we also need the velocity vectors of these two vector-valued functions. The velocity vector for this would be -5 sine t, 2 cosine t, and the velocity vector for the line would be 5, oops, I see a typo, -2. I wonder if my typo is going to continue. We're about to find out. I happen to be a human, can make mistakes. Clearly, that was a mistake. Unplanned, I'll be honest with you in video here. Now, we want to set up the line integral. Right. X and Y values. If our new integral is going to be in terms of t, as I mentioned, the line integral vector field dot product velocity vector with respect to t, I may have my velocity vectors, and I may even have t as a variable here, but that's not t. We only care about this vector field at points that are along the piecewise smooth path. We only care about the velocity vector along the path itself. Well, we have those functions. Here would be x and y as we travel along the ellipse, and here will be x and y as we travel along the line. And we have the velocity vectors for those. So when we set this up, here's the first part of our line integral. This would be the x value plus 3 times the y value, comma, the x value squared in the first path, the ellipse. And here's its velocity vector with respect to t, and we had a time interval from 0 to pi over 2. And now you might realize that pausing and rewinding is something that's necessary occasionally. Harder to do that in class. And for the line, the time interval from 0 to 1, the x value is 5t plus 3 times y, x value squared, and the velocity vector, yep, I did it again, missing that minus sign there, there would be our velocity vector. We would evaluate both of these line integrals separately and add them together to get the total work done by this vector field as a point moves along this path. That's one way of interpreting it. It is not the only use for this type of line integral, though. Alright, I did say set up but do not evaluate, so I believe we could consider this the end of that little story. Alrighty, hope that was somewhat beneficial, or at least to add to your repertoire of examples and tricks to use. Until next time.